Did you know the first KV-1 that reached Britain didn't look like a tank? It looked like a crime scene, dents the size of dinner plates, impact scars stacked on top of impact scars. 88mm hits, the kind that normally rip armor like cardboard, smashed flat as if the shell had punched a pillow. And here's the first microshock. Almost none of the hits went through. One British officer whispered, "This shouldn't be possible, unless the laws of metallurgy took a holiday." They had seen Panzer III's torn like tin cans, Shermans cracked like porcelain, even early Tigers split open under repeated stress. But the KV-1? This thing looked like it refused to die out of pure stubbornness. It broke a rule every engineer quietly believed. If armor is thick, it must be brittle. If armor is tough, it must be soft. You cannot have both. The KV-1 shattered that rule. When Lieutenant Merriweather pressed his finger into a crater left by a German shell, he felt heat. Heat, after days of transport. "Steel doesn't behave like this," he muttered. "This is wrong." And here comes another hook. The tank had taken more direct hits than most crews see in an entire war, and survived. Imagine telling a British engineer in 1942, your Matilda can survive 20 75mm hits, maybe 30, maybe even an 88 on a good day. They'd laugh. But here stood a heavy tank with the metallic equivalent of 50 fist-sized bruises, and not a single clean penetration. Did you know the Germans actually filed complaints about this? In their own archives they wrote, "KV armor behaves unpredictably under fire." Unpredictably, meaning infuriatingly resilient. This wasn't just engineering. It felt like the tank was cheating. And that's where the sense of injustice hit. Britain spent fortunes refining steel, perfecting alloys, running labs filled with PhDs. Meanwhile, a nation fighting for survival under constant bombardment somehow produced armor that outperformed Western designs, by accident or by genius. Which one was it? The British didn't know yet, and that uncertainty stung. So the order was simple: cut it open. Find the trick, expose the steel myth. Industrial saws rolled in. Cooling rigs activated, the KV-1 was wheeled into the metallurgical hall like a prisoner about to be interrogated. A researcher joked, "We'll find slag, cracks, impurities. You'll see. All brute force, no finesse." Another engineer didn't laugh. He pointed at a crater that should have shattered the plate, but instead looked like someone had hit warm wax with a hammer. "No, something's off. This isn't crude, this is engineered." Silence settled over the hall, dense and heavy like the armor itself. The sparks ignited, blades touched steel, and within seconds the British team realized even cutting the KV-1 wasn't going to be normal, to be continued. The moment the cutting rig touched the KV-1's armor, the British team knew something was off. The blade didn't dig in, it didn't bite, it screamed. The saw overheated almost instantly. They swapped in a stronger blade. 12 seconds, ruined. Another blade bent, another snapped. They had cut German, British, and American armor. Nothing behaved like this. Every time the saw tried to enter the steel, the KV-1 didn't shatter or spark wildly. It resisted. It pushed back. The armor acted like a single, stubborn, unified block of metal. Most steels soften as they heat. Others become brittle. But this steel did something no one expected. The hotter it got, the tougher it became. The technicians tried everything. Different speed, different angle, more coolant, less coolant. Nothing worked. The KV-1 wasn't being cut. It was testing them. When the first section finally peeled off, the engineers braced for the typical defects of rushed wartime production. Cracks, voids, uneven layers. There were none. The interior was smooth, uniform, consistent in a way that made the lab go quiet. The deeper they cut, the stranger the steel behaved. The inner layers looked softer, almost elastic, yet cutting them was even harder. It made no sense. Hard steels crack, soft steels slice. This armor ignored both rules. Under indentation tests, the weirdness only grew. Instead of channeling stress into fracture lines, the KV-1 steel absorbed the force, spread it sideways, and smoothed the impact like a shock absorber made out of metal. No micro cracks formed, None. German armor, under the same tests, produced webs of microscopic fractures. British armor showed fatigue lines. American armor split along grain boundaries. But this plate, nothing. Just a calm, stubborn refusal to break. One of the engineers finally stepped back and said exactly what everyone was thinking. This steel behaves like it knows it's better than us. No one argued. If the armor didn't rely on exotic alloys, and everything so far suggested it didn't, then the truth had to be hidden elsewhere. The team prepared the samples for the next stage, chemical analysis. If the KV-1's secret was in expensive elements, nickel, chromium, molybdenum, the machine would reveal it. If it wasn't, then everything they'd seen so far would become even stranger. The samples were sealed. The spectrometer warmed up. Numbers began to flash on the monitor. What the British were about to discover would force them to rewrite everything they believed about Soviet metallurgy, and it would be the last explanation they expected. To be continued. The moment the cutting rig touched the KV-1's armor, the British team realized something was wrong. The saw didn't bite. It screamed. The blade overheated almost instantly. They swapped it for a stronger one. It lasted 12 seconds. The next blade bent. Another snapped. It felt less like cutting metal and more like trying to scratch the surface of a frozen ocean. Every time the saw dug in, the armor didn't crack or splinter the way German or British plates usually did. It resisted. It pushed back. The KV-1 behaved like a single, dense, unified mass. Stubborn, cohesive, almost alive. Most steels under heat soften. Others become brittle. But this armor did something no one expected. It grew tougher the hotter it got. The technicians increased coolant flow, slowed the blade, changed the angle. Nothing. The steel kept behaving like a material that refused to acknowledge the rules it was supposed to follow. When the first plate section finally came off, a thick rectangular slice pulled away from the hull, the engineers leaned in, expecting the usual defects of rushed wartime production: gas pockets, cracks, impurities, uneven layers. They found none. The interior was disturbingly uniform, smooth, clean, flawless in a way that made no sense for a tank built in a besieged nation fighting for survival. Even more unsettling, the deeper they cut, the stranger the behavior became. The inner layers looked softer, more pliable, almost elastic, yet were even harder to cut than the outer shell. It defied the fundamentals of metallurgy. Hard steel is brittle. Ductile steel is easy to cut. You cannot have both in one plate, but the KV-1 did. The indentation tests confirmed it. Energy didn't travel through the armor the way it should. Instead of concentrating stress into fractures or crack paths, the steel absorbed the impact and spread it out, like a mechanical shock absorber built into solid metal. The technicians exchanged uneasy looks. They had tested German armor that crumbled, British armor that fatigued, American armor that split along predictable grain lines. But this plate, no micro cracks, no internal tearing, no signs of weakness. It held together as if it had been poured in a single perfect moment, a monolithic block that refused to break no matter how much force it endured. One engineer finally stepped back from the rig, staring at the armor as if it had insulted him. "What kind of steel behaves like this?" he said quietly. No one answered. The cutting was finished. The mystery was only getting deeper. Now it was time for chemical analysis, the test that should have revealed the truth. A scan of elements, a breakdown of alloys, the final definitive explanation for why this tank's armor simply refused to follow the rules of its time. And if the early signs meant anything, the results would be nothing short of impossible. The British metallurgists expected the chemical analysis to end the mystery. Steel composition doesn't lie. It reveals everything: the quality of the factory, the resources of the nation, the competence of the engineers. If the KV-1 armor was truly extraordinary, the chemistry would show it. So they shaved microsamples from the inner layers, sealed them in trays, and fed them into the spectrometer. The room went silent as the readings rolled in. Then came the shock. No high nickel content, no rich chromium levels, no generous molybdenum additions. None of the expensive alloying elements used by Germany, Britain, or the United States to strengthen their best armor. The KV-1 didn't have the chemical signature of a superalloy. It had the signature of a budget steel, the kind accountants approve, not engineers. The numbers were so ordinary, so unremarkable, that the junior technician thought the machine was malfunctioning. He reran the test. Same result. The armor that chewed through British saws, that bent blades, that refused to form micro cracks, was made from a composition so basic it bordered on primitive. One of the senior metallurgists stared at the data, pale and confused. "This can't be right," he whispered. "Steel this simple should fail like any other. It shouldn't behave like this." And yet, there it was. Low alloying, modest carbon, hardly any exotic elements at all. The team checked German samples for comparison. Nazi armor, especially early war high-quality batches, contained significantly more chromium and molybdenum, expensive additives meant to boost hardness and heat resistance. But KV-1 armor showed none of that. It was as if the Soviets had built an indestructible wall out of the metallurgical equivalent of bread flour. The explanation wasn't in the chemistry. It had to be somewhere else. The lead metallurgist leaned closer, tapping the datasheet with a finger. "If they didn't rely on exotic elements," he murmured, "then the secret must be in the treatment, the heat cycle, the rolling, the cooling." A quiet realization spread through the lab. This wasn't a story about a miracle alloy. It was a story about how the metal was handled, how it was shaped, tempered, stressed, relieved, forged, not what it was made from. And that made the mystery deeper. If Soviet factories really were under bombardment, understaffed, rushed, and resource-starved, how did they produce armor that performed like this? How did a nation with fewer industrial luxuries create steel that outperformed some of the most technologically advanced metallurgical facilities in the world? The team checked for traces of uneven heat treatment. None. Signs of over-hardening. None. Clues of cheap shortcuts. None. The KV-1 armor was consistent, balanced, stable, too stable. It implied a level of process control that the British didn't believe the Soviet Union was capable of. And yet, there it was. The steel told the truth. The strength of the KV-1 wasn't born from chemistry. It was born from process. A hidden method, a production rhythm, a thermal routine the British had never considered. A method that somehow created a plate of steel that defied the rules of its age. And now that chemistry had been crossed off the suspect list, there was only one place left to look, inside the microstructure. What they found there would be even stranger. When chemistry failed to explain the KV-1's impossible strength, the British metallurgists moved to the last place where truth can hide, the microstructure. If steel has secrets, they live under the microscope. The team prepared thin slices of the armor, polished them until they reflected light like black glass, etched them with acid, and set them under the lens. What they saw made one of the researchers exhale through clenched teeth. This isn't normal. The grain structure was tiny, not small, not refined. Tiny, the kind of microscopic consistency you'd expect from aerospace alloys decades later, not from a tank built in wartime Soviet conditions. Even more shocking, the grains were evenly distributed across the entire sample. No clustering, no random pockets, no disorganized growth, the signature of rushed heat treatment. The KV-1 looked as if its armor had been grown, not forged. This was the first impossibility. The second came minutes later. Under magnification, the steel revealed patterns that simply shouldn't exist in low alloy armor. Clean ferrite fields, smooth perlite bands, and a uniform carbon presence that refused to form the brittle networks seen in many German plates. German armor often carried stress scars, hidden lines where carbon clumped together, creating weak points waiting to explode under impact. The KV-1 had none. Not a single micro crack, not a single hard boundary ready to shatter. It was like staring at a textbook example of ideal steel, written by someone who had never read the textbook and somehow improved it by mistake. One of the metallurgists leaned back, eyes still locked on the lens. "This is controlled," he said quietly. "This level of grain refinement doesn't happen without a precise, intentional process." "But how?" another asked. "Where would the Soviets get the time, the tools, the precision during an invasion. It didn't add up, and yet the evidence sat on the optical stage, undeniable. The armor's internal structure behaved like a shock absorber. Impacts didn't travel in straight lines. They dispersed, bleeding energy across the grains, weakening the strike, dulling the edge of incoming shells. Instead of cracking, the steel flexed microscopically. Instead of failing catastrophically, it distorted in controlled, predictable ways. This wasn't brute force metal. It was forgiving metal, steel that refused to punish itself under stress. A material that turned deadly hits into manageable bruises. The British risked a direct comparison with a German Panther sample. Under the microscope, the difference was embarrassing. Panther steel, stressed, uneven, spotted with brittle carbide formations. KV-1 steel, calm, balanced, a frozen ripple of perfectly aligned grains. It didn't look like steel from 1941. It looked like something decades ahead. The lead scientist finally folded his arms and said the only thing he could. This isn't a miracle alloy. It's a miracle process. Someone, somewhere, figured out a heat treatment we don't understand. The room fell quiet. The chemistry was simple. The ingredients were cheap. The wartime conditions were harsh. But the microstructure, that was genius. And outside the microscope, sitting silent on its stand, the KV-1 hull suddenly felt less like a tank, and more like a message. The British now understood how the armor absorbed hits, but they hadn't yet tested how it handled real fire. That would be the next step, and it would be even more shocking. The British had seen enough under microscopes, enough sparks, enough broken blades, enough contradictions. Now they wanted the one thing no lab instrument could fake: impact. Real shells, real energy, real violence. They mounted a section of the KV-1 armor onto the firing range wall. A thick slab cut straight from the hull, still scarred from the saw fight. Across the field, gunners loaded a 6-pounder anti-tank round, a solid, proven weapon, the kind that tore through early Panzer IIIs like melted cheese. The order was given, the gun fired. The shell slammed into the KV-1 plate with a blast that shook the ground and did absolutely nothing the British expected. The impact crater was deep, yes. Violent, yes. But clean, predictable, devastating, not even close. A fresh layer of steel folded into a smooth depression. No cracking, no tearing, no internal fractures radiating outward. The armor had swallowed the hit like a heavyweight boxer absorbing a body punch. The gunners exchanged confused looks. A second shot was fired. Same distance, same angle, same result. No cracks, no spalling, no structural collapse. Just another bruise in the same impossible material. They switched to a 75mm, a shell that, by all logic, should have broken the plate open like a jawbreaker hit with a hammer. The gun thundered. The shell struck. And again, the KV-1 didn't surrender. The depression grew wider. Steel shifted, bent, compressed, but stayed whole. One of the officers muttered, "This thing doesn't fail, it negotiates." To push the limits, they fired 3 rapid shots at nearly the same spot, a death sentence for most tanks. Layer upon layer of stress should have torn the metal apart, but the KV-1's armor simply rippled, deformed, tensed, and held. The metallurgists ran up immediately, tracing the edges of the impact with gloved fingers. No sharp edges, no brittle fractures. Just controlled plastic deformation, a sign that the steel was redistributing the energy sideways, letting the force bleed out across the plate instead of tearing through it. German armor in the same test? It would have cracked. Sherman armor? It would have delaminated. British armor? It would have folded inward. But KV-1 armor acted like it had its own internal logic, a hidden rulebook for survival. And then came the real shock. They tested an angled strike, simulating a real battlefield scenario. A slightly off-center shot from the 75mm slammed into the plate, and the shell bounced. It ricocheted off the KV-1 with such force that one of the range technicians dove behind a crate as it skipped across the field like a flat stone across water. The range officer just stared at the armor and said, "Now we know why the Germans complained. Because this wasn't armor in the classic sense. It was a system, a whole-body shock absorber disguised as steel." Every hit spread through the microstructure, dispersing energy like ripples on a lake. Every blow was softened by a material that refused to break the way metals are supposed to break. The KV-1 didn't block shells, it digested them. With the test complete, the British were left with a tank that had survived artillery, saws, heat, pressure, and every rule of metallurgy they held sacred. Only one question remained. How did the Soviets create this? Under bombardment? With limited resources? On the edge of collapse? The answer would come in the final stage of analysis, and it would be the most unexpected discovery of all. By the time the firing tests ended, the British team had run out of explanations. The KV-1 had survived saws, microscopes, artillery, heat, impact, pressure, and logic. Everything they believed about wartime steel had been broken, bent, or outright mocked by this Soviet heavy tank. Now came the final stage, putting the pieces together. The metallurgists gathered in the lab, surrounded by charts, samples, impact molds, microscope slides, and the half-shredded blades of their cutting equipment. One by one, they laid out the evidence. Cheap chemistry, flawless grain structure, monolithic behavior, elastic shock absorption, no internal cracking, ridiculous resistance to heat, absurd performance under fire. Everything pointed to a single, unavoidable conclusion. A conclusion none of them wanted to say out loud. The KV-1's armor wasn't strong because it was exotic. It wasn't strong because it was advanced. It wasn't strong because it used rare metals, complex chemistry, or cutting-edge industrial tricks. It was strong because it was made differently. The Soviets had stumbled onto, or intentionally created, a manufacturing process the British had never seen before. A process built not around elegance or precision, but around brutal simplicity and enormous scale. The secret wasn't in the steel itself. It was in how the steel was treated. Slow rolling, long cooling cycles, heat treatment done in massive industrial batches, thick slabs forged under colossal presses that flatten grain boundaries into near-perfect alignment. Homogenization achieved not through finesse, but through sheer force and repetition. The KV-1's armor wasn't a technological miracle. It was an industrial accident that became a strategic advantage, a side effect of Soviet factories using gigantic, imprecise, but incredibly powerful equipment, machines that created steel with qualities no Western factory would ever have tolerated or even considered. The armor worked because it wasn't chasing perfection. It was chasing survival, and in that pursuit, it became something unique, a metal that refused to break according to the rules. The lead metallurgist finally said what everyone in the room was thinking. The KV-1 survived because the Soviets didn't try to make perfect armor. They tried to make armor they could produce in mountains. And somehow, that made it perfect. Another engineer added quietly, "No wonder the Germans were terrified. They weren't fighting technology. They were fighting a philosophy. A philosophy built on thickness over finesse, uniformity over elegance, process over ingredients, resilience over refinement." The KV-1 was the embodiment of that idea. A tank built not to win a contest of sophistication, but to endure a war of annihilation. When the final report was written, the British officers didn't use the word miracle. They didn't use superior, advanced, or revolutionary. They used one simple line: "This armor behaves unlike any steel known to us. Its performance cannot be replicated with our current methods." And with that, the mystery of the KV-1 was no longer a mystery. It was a message carved in steel. Strength doesn't always come from complexity. Sometimes it comes from the will to survive, frozen into metal.